Okay, so firstly, hello and welcome everyone to the Bitcoin Optech newsletter number 307, published on 14th of June 2024. And welcome to our weekly session titled Latest in Bitcoin Tech. So, as every week, we will go through the Bitcoin Optech newsletter and have a discussion pertaining what the newsletter contains. And we have this monthly Bitcoin Core PR review club that the newsletter covers, and it coincides with, I think, the third edition of the month, which is the one that we'll be going through. And other than that, we have the weekly release and releases and release candidates and notable core and documentation changes. So I'll just go through the preface of the newsletter. This week's newsletter announces a draft BIP for a quantum-safe Bitcoin address format and includes our regular sections with the summary of a Bitcoin Core PR Review Club, announcements of new releases and release candidates, and descriptions of notable changes to popular Bitcoin infrastructure projects. As I said, that we will probably not cover the news section, and I stated the reason for that as well. We will commence with the Bitcoin Core PR read this content and then go to the post as well, read it, and then try and understand what this PR is trying to achieve. In this monthly section, we summarize a recent Bitcoin Core PR Review Club meeting, highlighting some of the most important questions and answers. Click on a question below to see a summary of the answer from the meeting. Don't wipe indexes again when continuing a prior index is a PR by the charlatan that can improve startup time when a user restarts their node before an ongoing reindex has completed. Bitcoin Core implements 5 indexes. The UTXO set and the block index are required, whereas the transaction index, compact block filter index, and coinstats index are optional. When running with reindex, all indexes are wiped and rebuilt. This process can take quite a while, and it is not guaranteed to finish before the node is stopped for any reason. Because the node needs an up-to-date UTXO set and block index, the reindexing status is persisted on disk. When a reindex is started, a flag is set, and it will only be unset when the reindex is finished. This way, when the node starts, it can detect that it should continue reindexing, even if the user didn't provide the flag as a startup option. When restarting without a reindex after an unfinished reindex, the required indexes are preserved and will continue to be rebuilt. Before Bitcoin Core PR number 30132, the optional indexes will be wiped a second time. Bitcoin Core PR number 30132 can make node startup more efficient by avoiding the wiping of the optional indexes. So basically, this PR is about re-indexing. Okay. And as it mentions, there are 5 types of indexes that your software that are stored on your hard disk. Okay. 2 of which are required indexes, meaning they are mandatory. You don't have an option. Your node needs to store the data of those 2 indexes. Okay. The first is the UTXO set. It is indexed, and second is the blocks. The blocks are indexed, and there are 3 optional indexes, which is the transaction index, the compact block filter index, and the coin stats index. These are optional indexes. Okay. So what does this PR do? Let's click on the PR and just read through it. All right. I hope the font is implements 5 indexes. 2 are required. The UTXO set, that is Coins UDB, also often referred to as Coins DB, and the block index, that's the block tree database. The transaction index enabled with Jake index, a compact block filter index enabled with block filter index, and a coin stats index enabled with coin stats index. While running with reindex, all indexes are wiped out and rebuilt generally from the block files on disk. This process can take quite a while, and it can be aborted by the user before it is finished. Because the node needs to have an up-to-date UTXO set and block index, the reindexing state is persisted on the disk. When the reindex is started, a flag is set, and it will only be unset when the reindex is finished. This way, when the node starts, it can detect that it should continue reindexing even if the user didn't provide the flag as a startup option. This PR can be by avoiding the wiping the optional indexes when it is not necessary. All right. Yeah, as we discussed, there are five types of indexes which your Bitcoin Core node stores on your hard disk. Two of which are mandatory. That is the UTXO set and the block index. Okay, so each block is indexed, and the UTXO set is also indexed. And there are three optional indexes: the transaction index, the compact block filter index, and the coin stats index. uh, what happened, like up till now, what was happening is that when you were re-indexing your node or your database, okay, and for some reason the node shuts down, or it shuts down basically, not gracefully, okay, the mandatory indexes, that is the UTXO and the block index, okay, the state of these two indexes was stored on your hard disk, okay, and when you restarted, your re-indexing would restart from where you left it, meaning the previous state would persist on your hard disk. And when you restarted your node, you need not specify that re-index command, okay, you need not restart with your node with this re-index command. Even without that, your UTXO set and your block set indexes would be persisted, and they would be restarted from where you left off indexing when the node shut down. Okay, but as far as these three optional indexes, the transaction index, the block filter index, and the coin stats index, these three would be completely wiped off. Okay, so if you start re-indexing, let's say you start re-indexing with all of these five indexes, and for some reason midway before finishing re-indexing, your node shuts down. Okay, not gracefully, meaning you do not shut your node voluntarily. Could be a power cord, could be anything. Okay, and the node and the re-indexing is interrupted midway. When you restart the node, it will start from where you left off the UTXO set and the block index set. Okay, but the other three would be wiped off completely, and the re-indexing for the other three would commence from scratch. And also you have to restart your node with this re-index flag to restart the re-indexing of these three optional indexes from scratch. What this PR does is that it enables that the optional indexes also replicate the behavior of the mandatory indexes. So when you restart the node, okay, so when you're indexing, let's say you're indexing all the five indexes and the node shuts down for some reason and you restart, the state of not only the transaction of the UTXO set index and the block index are persisted on your hard disk, but also the state of your transaction index, your compact block filter index, and your coinstat index are preserved on the hard disk, and they are not wiped out, and the re-indexing commences from where it was at the point where it was when you shut the node, or when the node got shut down due to any unforeseen interruption. This is what this PR does. Okay, so it makes optional reindexes behave like the mandatory reindexes, and the optional indexes also now their states are persisted, and if you restart the node, the optional reindexes also start reindexing from where you left it, unlike before this PR, where the optional indexes would be completely wiped off. Only the mandatory indexes, that is the UTXO set and the block index sets, their state will be preserved on the hard disk. So there are some questions pertaining. Uh, okay, we did not read this completely. Let's just read the PR once. I mean the text, and then we'll go through the questions and answers. So don't wipe indexes again when continuing a prior index is a PR by the charlatan that can improve startup time when a user restarts their node before an ongoing reindexes happen. Bitcoin Core implements five indexes. The UTXO set and the block index are required, whereas the transaction index, compact block filter index, and coin stats index are optional. When running with reindex, all indexes are wiped and rebuilt. This process can take quite a while, and it is not guaranteed to finish before the node is stopped for any reason. Because the node needs an up-to-date UTXO set and block index, the reindexing status is persisted on disk. When a reindex is started, a flag is set, and it will only be unset when the is finished. This way, when node starts, it can detect that it should continue reindexing even if the user didn't provide the flag as a startup option. When restarting without reindex after an unfinished reindex, the required indexes are preserved and will continue to rebuild. Before Bitcoin Core PR number 30132, the optional indexes would be wiped a second time. Bitcoin Core PR 30132 can make startup more efficient by avoiding the wiping of the optional indexes when it is not necessary. So while reindexing, if the node gets shut for some reason and you restart it, you don't need to add this flag, this index command while restarting the node. Even without it, the node will detect that the last time it got shut down, it was in the process of reindexing, and it will by default automatically start reindexing, and it will not only process the state of the UTXO set and the block index, but it will also process the state of the other three optional indexes, and it will start reindexing them from where it left. This is what this PR does. So we just go through the questions that could come to your mind when you go through this PR. What is the behavior change introduced by this PR? Behavior is changed in three ways. First, as per the goal of this PR, optional indexes are no longer wiped again when the node is restarted before reindexing is completed. This aligns the wiping behavior of the optional indexes with that of required indexes. Second, when a user requests a reindex through the GUI, the GUI, this request is no longer ignored, reversing a subtle bug introduced in B47BD95. Third, the logline initializing database is removed. So there are two more changes. Firstly, this log line is removed from the terminal when you're reindexing. And secondly, I believe that using the GUI, you are not able to reindex any further. But now, due to a bug, due to the presence of a bug, which is fixed now. So these are the three primary changes introduced by this PR. The second question that could come to your mind is, what are the two ways an optional index can process new blocks? When an optional index is initialized, it checks if its highest block is the same as the current chain tip. If it is not, it will first process all missing blocks with a background sync through base index, start background sync. When the index catches up with the chain tip, it will process all further blocks through the validation interface, validation signals block connected. So basically, when you are trying to index blocks, there might be a possibility. There can be two things. Firstly, the first possibility is that your node is in sync with the current chain tip, and the second possibility could be that your node is not in sync with the current chain tip. If it's not in sync with the current chain tip, then it will first sync with the current chain tip, okay, and then start validating or indexing the blocks further. And if it's already in sync with the current chain tip, then it will just start indexing the blocks as they come in the future. How does this PR affect the logic of optional indexes processing new blocks? Before this PR, wiping the optional indexes without wiping the chain state means these indexes will be considered out of sync. As per the previous section, that means they will first perform a background sync before switching to the validation interface. With this PR, the optional indexes remain in sync with the chain state. And as such, no background sync is required. No background sync only starts after reindex has completed, whereas processing validation events happen in parallel. So this is what we had to cover in this weekly Bitcoin Core PR Review Club. Just to summarize, it is a PR that facilitates or that enables optional indexes to behave like the mandatory indexes. There are 5 indexes that a Bitcoin Core node maintains. One is the UTXO set, second is the block index set, third is the transaction index set, the fourth is the compact block filter index set, and the fifth is the coin starts index. Out of which two are required or mandatory, and three are optional, meaning your node has to maintain the UTXO set and the block index. These are mandatory, and the other three are optional. Okay, and up till now, what used to happen is that while reindexing, if your node got shut down for some reason and you restarted, only the UTXO set and the block index were persisted. Their states were persisted on your hard disk, and the other three optional indexes were completely wiped off, and they had to be started from scratch again. But now, after this PR is merged, if your node gets shut midway, the state of all the 5 indexes are persisted on your hard disk, and your node starts re-indexing from where it left when it got shut down. Any questions, any observations, any thoughts that anybody would like to share before we move forward?
Just a basic question: why is re-indexing required? What could be the situations where somebody would want to re-index?
One reason could be that while you are syncing the blockchain, you come across a corrupt block, and this happens very often. Has happened with me as well, and I'm sure it's happened with most people who run their nodes. And when you are syncing the blockchain, for some reason you come up against a corrupt node, and your syncing gets stuck there. And a remedy or a diagnosis to that is that you re-index. Okay, that corrupt block, that block is corrupt because of some error in indexing. The block is not being indexed properly. or the peer who is sharing you that block is sharing a block with inappropriate indexes. So you reindex it, and mostly that fixes the issue. Like when you reindex it, the corruption that might occur due to the block having an inappropriate index number gets fixed. So that is, I personally have come across only that one use case where you're syncing a block and you get a corrupt block issue where a peer shares and like a corrupt block with you, and you reindex all your blocks or your entire UTXO set. So the data that is persisted or stored on your hard disk is indexed properly.
Yeah, makes sense. Thanks.
Or
Faisal, uh, how does this like, for example, there are other indexes like Electrum and Fulcrum. So how does this affect that, or is it related?
no, this is specific to Bitcoin Core. I mean, I don't know if Electrum, like if it relies on Bitcoin Core for indexing. I'm not aware about that. This is specific to Bitcoin Core. I've never used Electrum.
Okay, okay.
Right. Hmm. Uh, all right. Anybody, like, we already have block indexes. Okay, we already have block indexes. So why do we need compact block filter index? Would anybody like to take a shot? Because we're already indexing all the blocks. Then why do we need to index the compact block filter?
Yeah, we need to do that so that we are able to serve compact block filters.
Okay. Right. Thanks. Hmm. Okay. Yeah, we're done with the Bitcoin Core PR Review Club. Let's move on to the releases and release candidates. Okay. So the first one is Core Lightning 24.05 is a release of the next major version of this popular Linode implementation. It includes improvements that help it better work with a pruned full node. C newsletter number 300 allows the check RPC to work with plugins. C newsletter number 302. Stability improvements such as those described in newsletters 303 and 304 allows more robust delivery of offer invoices. See newsletter 304, and a fix for a fee overpayment issue when the ignore fee limits configuration option is used. See newsletter 3 number 306. So basically, this release has a number of new features that have been added. Let's go through them. Okay, so the first one is it includes improvements that help it better work with a pruned full node. Okay, so what is this improvement that helps the core Lightning node work better with the pruned node? It adds support for retrieving required blocks from the Bitcoin P2P network if the local Bitcoin node has pruned them. Okay, so your Lightning node obviously does not have direct access to the blockchain, the Bitcoin time chain. It basically is connected to another Bitcoin node that provides it first-hand information about the Bitcoin time chain. Okay, and if your CLN node is connected with a Bitcoin node that is a pruned full Bitcoin node, and your CLN node needs information pertaining a specific block which has been pruned, from the Bitcoin node. So how do you access it? Okay, because if your CLN node is running a channel, for instance, where the funding transaction uh, is the transaction from any block number X, okay, and your Bitcoin node with which your Lightning node is connected has pruned that block with block X, which contains the funding transaction. So how does your Lightning node retrieve information pertaining it? Okay, so what that is the problem statement that this PR or this new feature solves. If the CLN node needs a block that has been proved by its local Bitcoin D, it will call the Bitcoin Core RPC get block from peer to request it from a peer. If the block is successfully retrieved, Bitcoin Core authenticates it by connecting it to the header it keeps, even for pruned blocks. Okay. So in this situation, what will happen? Your Lightning node is in need of retrieving information from a certain block, but the Bitcoin node with which your Lightning node is connected does not have access to that specific block because that block has been pruned. It's a pruned full block. It's a pruned full node. Okay, so in that situation, your Bitcoin node will trigger this command, get block from peer. Okay, and it will request its peer to send it that specific block which you are looking for. If the block is successfully retrieved, Bitcoin Core authenticates it by connecting it to the header. It keeps even for pruned blocks and saves it locally where it can be retrieved using standard block retrieval RPC. So even if the Bitcoin node with which your Lightning node is connected does not have a certain block which you are interested in or which your Lightning node is interested in, your Bitcoin node will now trigger this get block from peer command and request its peers to send that specific block. And once it receives that specific block, it will authenticate that block and store that block or the header of that block, using which any transaction in that block can be validated by your Lightning node, or information pertaining that transaction can be accessed by your Lightning node. So this is the first feature that has been added in Core Lightning 24.05. The second is it allows the check RPC to work with plugins. See newsletter 302. Okay, so the check RPC, what does it do? It makes the check RPC the lib plugin utility. I think what the check RPC does is that basically it checks whether an RPC is accepting valid arguments without actually triggering that call. So if you want to check whether an RPC command is functioning, whether it is accepting relevant commands and giving you back relevant information, and whether you want to check that the arguments that you intend to pass to a certain RPC are valid or not, you use this check RPC call. Okay, so this doesn't actually trigger the command. It just returns back information to you saying that the arguments that you have passed are valid. Okay, that's what it does. Let's see if we can see it formatted properly textually. Okay, adds a new check RPC that checks whether an RPC call uses valid parameters without running the call. Okay, so this is what it does. The check RPC call, it checks whether you have passed valid parameters, okay, without running the call. So if you don't want to run an RPC call and you want to check that the parameters that you intend to pass to that RPC call are valid, you can do that using check. Okay, and this has been incorporated in the latest release of Core Lightning 24.05. Allows the check RPC to work with plugins. Okay, let me see. I think I have notes if I have added something. That's it. It allows check RPC to work with plugins. Check RPC checks whether an RPC call uses valid parameters without running the call. Cool. So that is the second upgrade or second feature that has been added to this version of CLN. The third one is stability improvements such as those described in newsletters 303 and 304. What are those improvements? Adds an additional offset called chain lag into the HTLC time lock calculation. This allows HTLCs to target the current block height instead of the most recent block that the LN node has processed its sync height. This makes it safe for a node to send payments during the blockchain sync process. Okay, so we all know, like, I'm sure everybody here knows what an HTLC is. We've talked about it in depth during the Mastering Lightning sessions and also during the Optech sessions. So like HTLC, basically it's like like escrow account where you lock a transaction. Okay, you can unlock that transaction. Okay, I'm using very naive and surface level language, but you can unlock that transaction by either producing a proof that you are eligible to unlock that transaction, okay, which is the pre-image of a hash which locks that transaction, or there is a time delta. Okay, there's a time expiry. If you're not able to unlock that transaction, if you're not able to claim and redeem that transaction by providing the pre-image, then the transaction will go back to its initial tender. Okay, that's an HTLC, and it is time locked. It is like locked to a certain time span. Okay, and it is locked not based on the time that you and I use. It is locked based on the block height. Okay, so like for instance, if an HTLC is locked at time x, then it can be unlocked or it expires at time x plus n number of blocks. Okay, so the time lock is stipulated in the form of blocks. Okay, now what parameter do you use? Okay, so if I say that this HTLC expires after, let's say, 200 blocks, okay, when do those 200 blocks start? Because there is a possibility that my node is not in sync with the current chain tip, right? So like when does that time start? Does it start? What block height do I take into consideration for HTLCs? Do I take in consideration the block height of my node, or do I take into consideration the current chain tip? Okay, because if my node is not in sync with the current chain tip, what block height will be taken as parameter for unlocking the HTLC? My node's block height or the actual network's current chain tip? Okay, so this allows HTLCs to target the current block height instead of the most recent block that the LN node has processed. Okay, so because if in a Lightning network, like two Lightning partners, their nodes might refer to different block heights. Their nodes might not necessarily be in sync with the chain tip. So the standard procedure, or what is more recommended, is that the block height that is used is the actual block height. It is the current chain tip. So this is what this additional feature does. Okay, so it adds an additional offset called chain lag into the HTLC time lock calculation, which allows HTLCs to target the current block height instead of the most recent block that the LN node has processed. Its sync height. This makes it safe for a node to send payments during the blockchain sync process. Okay, so if your node is syncing, for instance, okay, this statement is very important. I noticed it just now. So if your node is syncing right now, okay, your node will take current block height. Okay, if your node is syncing, it's 1,000 blocks behind the current chain tip, and so your node will consider its chain tip, its local chain tip, to be the actual chain tip, in accordance with which it will lock the transaction, which is erroneous. Okay, so there might be a possible that your node is not in sync. It's in the process of syncing. So it's important that you don't take into consideration the chain tip of your local node, but you take into consideration the actual chain tip of the network, and you stipulate the HTLC time log based on the block height of the network instead of the most recent block that your LA node has processed. This is one 303. So this feature has been added. Okay, this chain lag that is taken into consideration. The second one is updates the fee rate security margin multiplier to dynamically adjust for a likely fee increases. The multiplier tries to ensure that channel transactions pay enough fee rate that they will be confirmed either directly for transactions that can be fee bumped or through fee bumping. The multiplier now starts at 2x current fee rate estimates for lower rates and gradually decreases to 1.1x as fee rates approach the daily high max fee rate. Basically, like this PR adds the fee rate multiplier. Okay, because we all know that in a Lightning channel, when you open like every time you update the state of the Lightning channel, you have to update your commitment transaction. Okay, but you are not aware when will you close that transaction. There might be a possibility that you update your commitment transaction and you stipulate a fee in accordance with the fee rate of the network at that point in time where you have updated your commitment transaction, but you might not go on the mainnet for a long tenure of time, and by the time you go on the mainnet, the fee rate of the fee rate might differ exponentially. So this is a prevalent issue in the Lightning network, and that is why we have mechanisms like anchor outputs. Okay, so like what this PR does is that it allows the fee rate to multiply. Okay, the fee rate will gauge the current market fee, and it'll like adjust the fee that is to be paid for the commitment transaction accordingly. Okay, so like the factor by which the fee rate multiplies is mentioned here. Okay, because initially the fee rate is expected to be which is a standard commitment transaction generally has a very nominal fee stipulated, because it is assumed that by the time you go mainnet, there is a high possibility of an exponential appreciation or decrease in the fee rate, and that is why when you go on chain, there are mechanisms for you to adjust what fee you want to pay to go on the mainnet. So generally, the fee that you pay for the commitment transaction is very low, because you eventually have to adjust it. So because the fee rate initially is very low, the initial rate of multiplication is double. So you double the fee rate and see whether the fee rate is adequate to for the transaction to be mined on the mainnet. And then slowly and gradually, as the fee rate goes on increasing, you reduce the factor by which you multiply the fee rate to go on the mainnet till the final factor with which you multiply is 1.1x. And then when you reach the max fee rate, which both the channel partners have mutually agreed upon, you can. Okay. So from the initial fee rate, you keep on increasing by a factor of 2x, and as the fee rate goes up, you keep reducing this factor till you reach 1.1x, and then you only increase the fee rate by a factor of 1.1x. And then when you reach max fee rate, then you cannot increase it any further. So this is another feature that has been added in the latest release of Core Lightning. It's covered 3 or 4 features. What's the next one? Let's see. Allows more robust delivery of offer invoices. See newsletter number 304. Would anybody like to take a shot on what offers are? They're also known as what's the second name? What's LX equals? Anybody remembers? Offers. Oh wow, it's showing Flipkart offers. It's known as a Boltwell invoice as well, but it's another name which I can't recall right now. Okay, I'm not able to recall, but there's another name for it. Offers bolted 12 invoices, and there's another name. Okay, fine. So all right, let's just read through what offers are. Offers is a proposed protocol enhancement for Lightning that would allow nodes to request and receive invoices over LN. An example of a common use of this protocol would be that a merchant generates a QR code, the customer scans the QR code, the customer's LN node sends some of the details from the QR code, such as an order ID number, to the merchant's node over LN. A merchant's node returns an invoice also over LN. The invoice is displayed to the user who agrees to pay, and the payment is sent. So up till now, like the invoices were not being sent over the Lightning network, right? The invoices were sent outside the Lightning network. Like for instance, on the Bitcoin network, if you want somebody to make a payment to you, you can't send them your Bitcoin address over the Bitcoin network. Okay, and send it to them outside the Bitcoin network. So if Alice wants to pay Bob 1 Bitcoin, Bob will have to send his address to Alice outside the Bitcoin network, either in the form of like a paper or an email or a screenshot or a text SMS or whatever. Okay, but there's no provision for two people to share their addresses to receive payments on the Bitcoin network. And the same was the case with Lightning. Like if you wanted to make a Lightning payment to someone, you had to copy your Lightning address and send it to them via text, or you had to share the QR code with them over the internet or WhatsApp signal, whatever. Okay, but now the invoices like Bolt 12 offers enable sharing invoices over the Lightning network. Okay, although the above use case is already addressed today by using Bolt 11 invoices, the ability for spending and receiving nodes to communicate directly before attempting payment provides much more flexibility. For example, the requested amount would be specified in the terms of a non-Bitcoin currency, example USD. If the BTC to USD exchange rate changed too much since the invoice was received, the two nodes could automatically negotiate an update to the payable BTC amount to make it again consistent with the requested USD amount. So all of this interaction is happening between the two nodes over the Lightning network. Interactive communication between the nodes also enables features that aren't possible with both 11s, a one-time use hash lock, such as recurring payments for subscriptions and donations. So previously, like the two nodes would only interact with each other on the Lightning network once the invoices have been sent and the channel has been established. But Bolt 12 invoices facilitate interaction between two Lightning nodes even before a channel has been established between them. Like they can negotiate the payment terms even before the Lightning channel has been established between them. So what is the upgrade? It adds stability improvements such as okay, it allows more robust delivery of offer invoices. Okay, let's see the newsletter. We opened it. Right. It adds a reply flow to offer style invoice requests when it can't find a path to the reply path node. CLN's connectd will open a transient TCP/IP connection to the requesting node to deliver an onion message containing an invoice. This PR improves core Lightning's interoperability with NDK and allows using onion messages even while only a few nodes support them. So I believe what this means is like when two Lightning nodes are trying to establish it, like trying to share Boltwell invoices with each other, and one node cannot find a path to another node. Okay, what happens is that those two nodes establish a connection with each other using the TCP IP protocol. Okay, and they share the invoice over this TCP IP protocol, and once the invoice has been shared, uh, they again discontinue the connection with each other, and after that the connection is established over the Lightning network. Okay, let me just validate that if I have something. Yeah, okay, I'll just read through it. Allows more robust delivery of offers. Offers a protocol for Lightning that would for Lightning that would nodes to request and receive invoices, that allows basically nodes to request and receive invoices over LN. If a sender can't find a path to the receiver but knows the receiver's network address, the sender can simply open a direct peer connection to the receiver, send the message, and then optionally close the connection. So you don't need the receiver of the payment to share an invoice with you. Like the sender can directly initiate the process if it knows the receiver's network address. It can establish a connection with it. Okay, and uh, request for a Boltwell invoice. Okay, let me see if there's something else to cover in this, and then we can see if we have any questions. And a fix, this is the last one, and a fix for a fee overpayment issue when the ignore fee limits configuration is used. So yeah, this ignore fee limits configuration is basically when you are routing a payment, I believe over the Lightning network. Okay, there are some fee limits that you stipulate, like the minimum fee and the maximum fee, etc. Okay, if this ignore fee limits is triggered, then those fee limits that you've set will be overlooked. It will ignore those fee limits that you have already set. So this changes the behavior of Lightning D to ignore the ignore fee limits setting during a cooperative channel closure. This fixes an issue when a co-Lightning channel opener node overpays fees when the counterparty is an LTK node. In this scenario, when the LTK non-opener node Alice initiates a cooperative channel closure and begins fee negotiation, the CLN opener node Bob the CLN opener node Bob responds that the fee can be anything between minsats and max channel size due to the ignore fee limits setting. NDK will always select the highest allowed amount contrary to both specification. So Bob picks up the upper bound and Alice accepts, resulting in Alice broadcasting a transaction which considerably overpays. Okay. So if this ignore fee limit is triggered, okay, then the among the two partners that initiates the cooperative close, it's obvious that they are more in need of closing the channel. Okay, and they if this ignore fee limit is triggered, then they will choose a higher fee. They will ignore the fee limits and they will choose a fee as high as they can to ensure that the channel is closed as quickly as possible and they can redeem their funds on the mainnet. Okay, so this latest release of Core Lightning ignores the ignore fee limit. Okay, it ignores the ignore fee limit and ensures that the fee limit is between the min sats and the max channel size. These are four or five improvements or features that have been added to the latest release of Core Lightning 24.05. Okay, so yeah, any questions or any thoughts or anything anybody would like to share pertaining this new release, which has a lot of features? All right. No questions. Let me see if there are some questions that I can ask. Allows the check RPC stability improvements or all right. Would anybody like to take a shot at what's a prune node and why is a prune node called a full node? What's a prune node, and if it's prune, why do we call it a full node?
So a pruned node is a full node which validates all transactions and blocks, but only after a certain block height that the node user can set. So it does not have the entire blockchain from the genesis block till the chain tip. It has a specified block height from the specified block height to the chain tip.
Right. So, as you said, that the Pruned node does not have the entire blockchain history. Like it does not store all the blocks from the Genesis block. Right. It stores certain blocks and it skips certain block. It does not store the entire blockchain history. So why do we call it a full node? This is a question that I always had.
Right. I think
Because before pruning, it does the job as full node does. Like it verifies all the blocks, and only after it does the job does verify all the blocks does the pruning happen.
Right. So yeah. I mean, yeah, do things like firstly, yes, that it validates the entire blockchain, and only after that it prunes. That's why it's a full node. And also, even after pruning, it performs all the tasks that a full node performs. Okay, like what are the three primary tasks that a full node performs? Right. The full node firstly validates all the transactions and validates all the blocks. Okay, it gossips all the transactions, it gossips all the blocks, and it gossips addresses on the network. A pruned node, even though it does not contain the entire blockchain history, it validates all the transactions. Okay, even after being pruned, it validates all the blocks even after being pruned. It gossips all the transactions that it has validated even after being pruned. It gossips all the blocks that it has validated even after being pruned, and it also gossips all the addresses that it sees even after it has been pruned. So it performs all the tasks of a full node. Okay, and this is a confusion that I personally had. And I think this was also a question in one of Bitshala's cohorts. I can't remember which it was, that whether a pruned node is a full node or it's not a full node. And there was a lot of discussion about it. And even I wasn't clear. So, but now I know and we know that a pruned node is a full node. It does not have the entire blockchain's history. But if somebody asks you or you read somewhere, or if it's asked in any of the cohorts, then we know now that a pruned node is a full node. Cool. Then the second release is which one? Bitcoin Core 27.1 is a maintenance release of the predominant full node implementation. It contains multiple bug fixes. So yeah, nothing much to talk about it. This new release contains bug fixes. What bug fixes is not mentioned in detail. So you can probably check it out to see what bugs have been fixed. Cool. So we're done with the releases and the release candidates in the PR review section as well. We'll come to the final section, notable code and documentation changes. Let's see how much of it can we cover. Probably not the entire thing. Bitcoin Core PR number 29496 bumps TX max standard version to 3, which makes topologically restricted until confirmation TRUC transactions standard. If a transaction's version is 3, it will be treated as a TRUC transaction as defined in the BIP 431 specification. The current version remains 2, meaning the wallet will not create TRUC transactions yet. TRUC transactions is a new name or a more recent name given to transactions that have version number 3 or that will have version number 3. Would anybody like to take a shot at what TRUC transactions are? Or at least what TRUC transactions are also known as? Transactions with version number 3. They are known as V3 transactions, and we've talked about them in detail, V3, but now they're known as TRUC transactions. We talked about them in like lot of detail. Where is it? Where is it? Proposed by Gloria Zhao. Yeah, and they can't mention it here, but yeah, initially they were known as V3 transactions because these are the transactions that have version number 3. They were non-standard, but now they're standard, and now they're known as TRUC transactions. So V3 transactions or TRUC transactions are one and the same. TRUC transactions are topologically restricted until confirmation. Okay, so basically, V3 transactions or TRUC transactions are transactions that can have only one child. Okay, that can have only one unconfirmed parent. A V3 transaction or a TRUC transaction is a transaction that can have only one unconfirmed parent, and the transaction in itself cannot exceed, I believe, 100 bytes. V3 or version 3 transaction relay is a proposal to allow transactions to opt into a modified set of transaction relay policies designed to prevent pinning attacks. Yes, it prevents pinning attacks. Combined with package relay, these policies help enable the use of dynamic fee rates with hidden on-chain transactions, V3, see, they were referred to as V3 transactions earlier. V3 transaction relays a superset of standard transaction policy. That is, V3 transactions follow all rules for standard transactions, example, minimum and maximum transaction rates, while also adding some additional rules designed to allow transaction replacement while precluding transaction killing attacks. V3 transactions also require minor changes to the package RBF policy in order to maintain incentive compatibility with miners. V3 transaction really solves a rule 3 transaction pinning and may allow the removal of CPFP carve out. Yeah. So like if you want to completely understand what problem are V3 transactions or truck transactions solving, then you can check out what a CPFP carve out is. Like firstly, we need to understand what pinning is, all right? So you can go through what transaction pinning is. Earlier, transaction pinning was solved by CPFP carve out, okay, and the usage of ephemeral anchors. Now transaction pinning is being combated with truck transactions, okay, such that one unconfirmed transaction cannot have more than one unconfirmed child. One unconfirmed transaction in the mempool cannot have more than one unconfirmed child in the mempool, and the child cannot be in excess of 100 bytes, I believe. So these are what truck transactions are. So what does this PR do? It bumps the TX Max standard to version 3. So up till now, the standard versions for transactions were only up till 2. So if your node saw any transaction which has a version number higher than 2, it would consider it to be a non-standard transaction. But now even 3. If your node sees a transaction with version number 3, it will still treat it to be a standard transaction. Okay, so if it sees a truck transaction, a V3 transaction, now standard transactions. Okay, if a transaction's version is 3, it will be treated as a truck transaction as defined in the BIP 431 specification. A BIP number was recently allotted to truck transactions, and its BIP number is 431. The current version remains 2, meaning the wallet will not create truck transactions yet. So I believe Bitcoin Core wallets will not create truck transactions or V3 transactions, but if they come across a V3 transaction having version number 3, they will treat that transaction as a standard transaction. All right. Any questions for reading this VR? Cool. If none, then let's move forward. Bitcoin Core PR number 28307 fixes a bug that imposed the 520 byte P2SH maximum script limit on SegWit redeem scripts for both P2SH SegWit and Batch32. This fix enables the creation of multisig output descriptors involving more than 15 keys, now allowing the Optech multisig consensus limit of 20, including signing for these scripts along with other post SegWit redeem scripts that exceed the P2SH limit. So P2SH transactions, I mean, would anybody like to take a shot at what's a P2SH transaction? Anyone?
So they are pay to script hash, it's called. So instead of while a pay to public key hash is a type of a script, you can include any other type of scripts that are non-standard, like that are non-standard, which are not like a typical pay to public key hash, and you can put that script, whatever it may be. Most used pay to script hash scripts are of multisig types. So that is so that's what scripts are, and you hash the script, and then you create an address out of it. So that is a pay to script hash type.
Right. And what you said brought me to a question. You can put a P2PKH in a P2SH. Okay. Isn't that correct?
Yeah, we
Right.
can.
Yeah.
No matter what it.
Right. Okay. Yeah. So basically, we can. I mean, if in a multisig script, we can either use a bare multisig script, okay, or we can use P2SH. Like bare multi scripts, generally, I think the standard bare multisig script currently in Bitcoin Core is 3 of 3. Anything above 3 of 3, bare multisig script is considered to be non-standard. Anything above that has to be P2SH. Okay, but even for P2SH, there are some limits. Okay, what's P2SH? It's basically pay to script hash. Okay, so if there's a multi-sig script, generally the script is contains of multiple public keys. Okay, and to unlock it, you need multiple digital signatures. So the script carries a lot of weight. So what you do is you hash the script. Okay, you hash the script, and only when the spender needs to spend the script, produce a redeem script. Okay, they need to produce a redeem script. So the maximum height of the redeem script of a P2SH transaction is 520 bytes. So any of you who've gone through mastering Bitcoin know what P2SH is. Okay, if you go to Bitcoin Core's code base, I can't remember which file that is. If you go to the file, I think it's script.cpp. I'm not sure. Okay, if you go to that specific file, you get a list of standard scripts. Okay, and you'll see that P2SH is a standard script as long as its redeem script is of 520 bytes or less, and as long as it contains 15 public keys. Okay, so like maximum a P2SH script for it to be considered standard, it need not have more than 15 keys. Okay, for a bare multi-sig script, for it to be considered standard, it cannot have more than 3 public keys, and for a P2SH redeem script, for it to be considered standard, it cannot have more than 15 keys. Okay, this is for P2SH. So what happened is that this PR fixes a bug that imposed the 520 byte P2SH maximum script size limit. So a P2SH script's redeem script can be of maximum 520 bytes on SegWit. Okay, this is P2SH, but due to a bug, this restriction was also being imposed on SegWit. That is, I believe, P2WSH. Okay, for both P2SH SegWit and Bash32. Okay, this fix enables the creation of multi-sig output descriptors involving more than 15 keys, now allowing up to the Optech multi-sig consensus limit of 20. So instead of like it lifts this PR lifts this limit of 520 bytes from P2WSH transactions. Okay, and P2WSH transactions are not now restricted to the size of the script. Rather, it is restricted to the number of I mean these signature operations of check multisig. Okay, which is up to 20. So the P2WSH script can now be of a size greater than 520 bytes as long as it does not have more than 20 object multisig opcodes in it, including signing for these scripts along with other post-segwit redeem scripts that exceed P2SH limit. Okay, let me see. We can look at the PR. Okay, I don't think I'm able to find it. Cool. No, I'm not able to figure out. It was this PR or some other PR, I don't remember, in which it was explicitly mentioned that I mean that limit was specifically mentioned. Anyways, yeah. So basically, broadly, that is what it is. Okay, so the P2WSH is not restricted to 520 bytes, rather it is restricted by the number of Optech multisig, in which the consensus limit is 20. All right, cool. The second one is done. Let's take the third one, which is also related to Bitcoin Core. Bitcoin Core PR number 30047 refactors the model of the Bech32 encoding scheme, a char limit from a constant of 90 to an enum. This change allows for easy support of new address types that use the Bech32 encoding scheme but don't have the same character limit as BIP 173 was designed for. For example, to enable passing silent payment addresses which require up to 118 characters. Okay, so Bech32 encoded Bitcoin addresses had a character limit. Okay, they could not exceed 90 characters. Okay, but now what happens is as we move forward, like new payment mechanisms are being introduced. Okay, new address formats are being introduced. Okay, so a silent payment address can go up to 118 characters. So what this does is that if a silent payment address goes up to 118 characters, it cannot be encoded in Bech32 format because the Bech32 format has a character limit of 90 characters. And if you encode a silent payment address in a Bech32 format, and if it is which means it can't go above 90, right? But for silent payments, your address can go up to 118 characters. So now instead of hard coding the character limit for a Bech32 encoded Bitcoin address to 90, and enum is provided, which probably will contain all the possible payment mechanisms and determine which specific type of payment address this is, and allow the Bech32 encoding scheme to be up to to change or to use the number of characters that that specific format of address requires. Okay. Let's see. So it lists that 90 character limit from base 32 encoded addresses. Yeah, see, 90. Okay. So like we have this string dot size. I think this string is the address. So we have a reference. We have a reference to a string. Okay. And this string is the address. We have a reference to the address. Okay. And we're checking the size of the address here. Okay. We're invoking the size method on the string, which is the address, and it cannot be more than 90. Up till now, it was stipulated that it was hard coded that the base 32 encoded address cannot exceed 90 characters. It was hard coded, but now we've changed that. Okay, we've changed that to limit, which I believe, I don't know what this limit is. I think it fetches the value of limit from an enum. Fetches the value comment from an enum. It's coded to, as you can see, this is the previous code where the base 32 encoded. Okay, like base 32 and base 32M, they were hard coded to have a character limit of 90, but now the hard code limit is removed. Okay, and this variable is there, which I believe is its value is determined from an enum. So it can be more than 90. For instance, if it's a silent payment address, you can encode it in base 32 format, and it can be of more than 90 characters because silent payment addresses can go up to 118 characters. Okay, that is what it does. So we're at 9.3. Let's take one what do you say? Document code and documentation change, or one PR from the Lightning Network. Let's take this one. Let's take this one. LND PR number 8491, add CLTV expiry flag on the LNCLI RPC commands, add invoice and add hold invoice to allow users to set the min final CLTV expiry delta. The CLTV expiry delta for users. No case for changes on the pull request, but it could be in response to LND recently raising its default from 9 blocks to 18 blocks to follow the bold QO specification. Okay. So LND, I'm assuming most people here know what's the CLTV expiry delta. Okay. What's the CLTV expiry delta? Like when you are routing a lightning payment through multiple hops, okay, like each participant or each router in the Lightning Network gets a time frame within which they need to furnish a pre-image to redeem the funds that they are eligible for. Okay, and for the time that is given to relayers of the Lightning transaction is less. Okay, so that difference or that disparity in the time that is given for them to furnish the pre-image is referred to as the CLTV expiry delta. Okay, which was 9 blocks. So it kept on increasing by 9 blocks. So if Alice sends the payment to Bob, Bob sends it to Charlie, Charlie sends it to Dan. So Alice gets the time of 9 blocks more than Bob, who gets 9 blocks more than Charlie, who gets 9 blocks more than Dan. And now it was updated to 18 blocks. Okay, and now LND, what this PR does is it adds a CLTV expiry flag on the LNCLI RPC commands, add invoice and add hold invoice to allow users to set the min final CLTV expiry data. We have a version of min final CLTV expiry data to vary from what the default initial value was. Okay, this PR is specific to LND. And yeah, I think we're done for the week. This is all that we'll be able to cover because the news article will take a lot of time, and the other code and documentation updates will also take a lot of time. I'll just read through this uh, news article if there are any quantum computing buffs here who would like to go through it. It's like really fascinating if you get time and if you want to delve into it. So developer Hunter provide post to both Delving Bitcoin and the mailing list a rough draft BIP for assigning version 3 segment addresses to a quantum resistant signature algorithm. The draft BIP describes the problem and links to several potential algorithms along with their expected on-chain size. The choice of algorithms and the specific implementation details are left for future discussion, as are additional BIPs necessary to fully realize the vision of adding full quantum resistance to Bitcoin. So up till now, we know that Bitcoin addresses are safe because the discrete lock problem of the elliptic curve has not been solved deterministically, right? So you take a public key of yours, which is a scalar number. You perform scalar multiplication between your private key and generate a public key. Okay, and doing the reverse of that deterministically is not possible. Randomly through brute force it is feasible, but deterministically it is not possible. Okay, that is what gives Bitcoin the public keys its strength, or Bitcoin's address is its strength, right? Because you reveal your public key if you're paying to a P2PK address, and you reveal your public key if you're paying to a P2TR address. Okay, so all P2TR addresses and all P2PK addresses reveal their public keys. Okay, and if it is deterministically possible for a quantum computer to find the private key from the public key, then Bitcoin's address security gets compromised. Okay, so this proposal basically talks about what can be done if quantum computing tomorrow manages to break ECDLP, that's elliptic curve discrete block problem, and quantum computing is able to find deterministically the private key using the public key. Okay, then all the public keys that are available on the blockchain are vulnerable, and their private keys can be accessed. So like this news article proposes, or this developer has proposed a solution to that, and he calls them I think it's P2QRH address. Okay, that's P2 quantum resistant hash. So we have like P2PK, we have P2SH, we have P2WSH, we have P2WPKH, we have P2TR. Okay, so this address he refers to it as P2QRH, that is P2 quantum resistant hash. So these addresses will be quantum resistant as per the proposal. So even if the ECDLP elliptic curve discrete block problem is broken, the bitcoins whose public keys are revealed in the blockchain can still be safeguarded from quantum computing attack. So like whoever wants to dig deep into it can go through this article and dig into what is Grover's algorithm and what is Shaw's algorithm, and what how quantum computing works, and how exponentially large numbers are factorized using Euclid's algorithm. But we will not be able to cover this in the session because that will take a lot of time. So I just thought I'll just give an overview of what this news article is about. So if it triggers somebody's curiosity, they can go through it on their own. So from my end, this is what I had to share for this week of news. If anybody has anything to share, any queries, any questions pertaining specifically to what we've covered about in this newsletter, please feel free to go ahead and ask your questions or share any thoughts that you'd like to.
Yeah, like basically this P2QR focuses on your on the risks of an ECDSA being broken. Am I right?
Right.
Okay.
And I think it goes a step further. Okay, like for instance, there's a P2PK transaction. Okay, now let's say the coins that Satoshi owns. Okay, the coins that Satoshi owns are to the P2PK address, right? P2PK address. So the public key is known. The coin that Satoshi owns, its public key is known. So if quantum computing breaks ECDLP, okay, and is able to find deterministically the private key using a public key, all those coins that are on the blockchain whose public keys are exposed, like P2PK transactions and P2TR transactions, all those coins can be stolen, right? And a lot of those coins for which the owners might not even be available. Right? For instance, the 1 million bitcoins that Satoshi owns, I believe I'm certain that those coins belong to a P2PK address, okay? And you can't even transfer it to a P2SH address or any other address because the key is not available anymore, right? Those are susceptible, and all coins which are on a P2PK address or a P2TR address where the owner or the claimant is not available, all those coins are available for people to be stolen. Okay, so I believe this P2QRH this address format goes a step forward, and it proposes a mechanism through which those coins which belong to P2PK addresses can be sent to P2QRH addresses. Okay, can be sent to PQRH addresses, thereby safeguarding those bitcoins, even if the owner who possesses the private key is not available. So you cannot access those bitcoins, but you can send them to a P2QRH address. That is what I believe. That is what my surface level understanding was. But this is in a very premature state. Okay, there's no quantity available about not a lot was even shared in the Optech newsletter podcast. Not even a bit has been drafted about it. Okay, it's just the brainchild of this developer that he shared, and the only information that we have available in this post. And even in this post, he's mentioned that in the coming weeks he'll keep on sharing the progress of what work he's doing. But up till now, there is very little information. This is all the information that we have from year to year,
So,
and probably this article.
anyway, if at all we create a new P2 QRH type of address, then the existing holders of a P2 public key P2 PK addresses, they have to migrate, like move their coins send their coins from this address to the new type of address.
Right.
Am I right?
Right.
So
Then all the
how is it
transactions, all
possible
the bitcoins, yeah,
without signing?
without.
Without signing, like I own a P2 PK address on the head, and I have some sats on it. So I have to actively go and draft a transaction from my P2 PK to the P2 QRH address. Am I right?
Yes, what you're saying is makes complete sense. Yes, that is the only way. But like one question that I have in mind, okay, is that what about the bitcoins that have been sent to a P2PK transaction and the owners are not available? Like, how do we secure those bitcoins? Is it possible? Like does this have any solution to that? Because if I have Bitcoin that is on a P2PK address, right, and I can send it to a quantum resistant address, right? But there are so many
Yeah.
Bitcoins, especially during the early days, which are abandoned where the owners are not accessible, right? Those coins will be up for steal. So, like, what do you do about that? Just going through the article, I felt that this proposal has a solution to that as well. I did not go into the very details, intricate details and nuances of it because it doesn't even have, by the way. Okay, so I spend most of my time trying to understand this what you call the Shaw's algorithm. Okay, Shaw's algorithm is a way that optimizes uh, uh, basically if you want to break DLP, okay, Shaw's algorithm is a mechanism that makes it exponentially faster. Okay, using Shaw's algorithm, you can break the discrete law problem exponentially faster. Okay, using quantum computers.
Yeah.
But I just browsed through this article. I got a feeling that this fellow also has a solution to the coins that are locked to a P2PK address where the owner is not accessible because somewhere he touches about Satoshi's coin. Somewhere in this article, he touches about Satoshi's coin, and I don't understand what would be the reason to talk about Satoshi's coin when Satoshi's not here. Maybe it was a misunderstanding on my part, or maybe he does have a solution for the coins that are on P2PK address. I'm not really aware about that. But yeah, anybody who's curious can dig into it.
Okay.
All right. All right, cool. Anything else to say, or I can stop sharing my screen?